Hey, welcome back to Graduate Statistics. That's week 13, lab 13, lab video 3. And we are working on this problem where we would like to predict current milk production from some variables that a specialized cooperative collected. So there's a data set that we were given, and we explored that data set. We identified some candidate predictors that showed some stronger correlations with current milk production individually when analyzed pairwise. And now we need to dig deeper and confirm that these correlations are not only, higher than 0.30, but also statistically reliable. So we're going to run a correlation analysis and kind of print a correlation matrix. But that only works with continuous variables. So I'm using, I'm applying the R correlation function. As input, we have to say that we want a matrix. So we want pairwise correlations between all variables inside the milk data set. So this is the piece you need to change if you want to do that with a different data set. And you also need to say that you want to look at all lines. If that's the case, in this case, we want to look at the 9 and 9. Observations, and we just want to look at the first 6 variables because the 7th variable is categorical and it wouldn't make it work. So if we look here, I need to ask to print, sorry. We have our correlation, interesting. We have our correlation, oh, I know what I mean. So we saved that correlation analysis inside an object called CORR. Now we want to print the correlation matrix with the R values and with the P's. So one matrix with the R coefficients, which we already know from the previous plot, and one matrix with the p-values. I'm just putting them side by side so you can know what p-values refer to what. So to print the R values, you want to call the object and say that you want the R. To print the p-values, you want to call the object where you saved the correlation and call p. But I want to round it out with just 2 decimal points. So I'm applying this round function on top of it. So I'm asking R to round the R coefficients to 2 and the P coefficients to 2. And here's what I find. So the variables that we're interested in, so we saw correlation between current and previous milk production of 0.74, and it is statistically reliable. It's less than 0.001 minimally, so easily less than 0.05. We also are interested in this correlation here between current milk production in days. So you see it's almost negative 0.50, and it is also statistically reliable. So even if we're not going to use the numerical variable days, if we're going to use the categorical variable, remember they're measuring the same thing, so it gives us hope that together they could be good predictors. So I'm going to pick my final variables. I'm going to pick variables that are meaningfully, so it's easy to measure, it's something you're interested in, and statistically correlated, right? So P needs to be less than 0.05. And predictors should have low correlations with each other. Attention when it's more than 0.6, definitely leave it out if it's more than 0.8. There are specific diagnostic tests that you can run, but it's sort of beyond the scope of this course. Okay, so let's focus on the 2 predictors with the strongest relationships to the variable, since we saw that there's hope that they can help. We're looking at the variable previous and number of days since lactation. We have to pick one of the variables that measure the letter, either days, which is numerical, or I79, which is categorical. And as I said at the beginning of this lab, I'll pick the I79 first to match the kinds of models we discussed in class. For the next round, maybe the first one next time, I'll use the variable days so that you can see, what we may miss if we can't separate into into two lines. So it's nice when we can have a categorical variable and a numerical variable because we can still nicely describe it with a plot, with a scatter plot. All right, so let's look at the best descriptive we can get. So I'm just getting a code for a scatter plot. You can grab it from, lab 4, from last lab. I'm using the function ggplot. Here is the milk data, and I'm going to put previous in the x-axis because that's predictor, current in the y-axis because that's the response variable, and I'm asking you to color with the other variable that I want to put in the model, which is the categorical variable I-79. So this is the piece that we really can't do if the second predictor is a continuous variable. We would have to do like a 3D plot. It's harder to visualize. So when you have more than one continuous variable in your model, it's hard to visualize in just one plot. There are some tricks, but it's more, we basically count on the numbers to guide us, not so much in visuals. Beyond the initial visualizations, pair by pair. Now I'm putting jump points because I want to create these little points to correlate. And just make sure if you grab it from somewhere else that you don't need color here. Because imagine if I remember I had color here, blue. Let's say I'm asking R to use color to code what's 0 and what's 1 in this categorical variable. If I pass another color here, it will color on top and make everything the same color. So be careful. Don't put color in here. You can do it if you have just one, if you had just X and Y. But if you're using color to distinguish two levels of a categorical variable, take it out of inside of here, which in previous labs we've been adding that to the scatter plot. So theme classic, the title is predicting milk production, previous and current. Current not found, huh? I think it's current milk, isn't it? Yeah, current milk, that's all. All right. Here's the scatter plot. So current is here. So we can see how when cows have less than 79 days since present lactation, the dots fall more on top, at least some of them, and they fall more on the bottom when I-79 is 1, when cows have more than 79 days. But it's interesting to see that really depends on the level of this variable here. For smaller values of production in the previous month, you see like these red dots on top. As you have more and more production in the previous months, you don't see that distinction, right? So the dots start falling in place. So they don't initially, but then they start falling in place. It's as though I would have a slope. I would start out here, up here, if I have cows with less time since last lactation, but then it would sort of converge with this other line. So if you recall the plot that we've seen correlating volume and weight of books, if you can't remember it, go back to the class slides. We would see that the relationship between weight and volume was pretty much the same for hardcover and paperback. The slope was pretty much the same, but one was kind of on top of the other. All dots were on top for a hardcover book compared to the other. Here, we see some red dots on top for low values of previous, but not for high values. So it seems that the effect of previous milk production on current seems to depend on whether you have cows that have just lactated or cows that have lactated for a longer period of time, right? Because just try to imagine if I were to fit a line here, that line would probably start up here and go here, right? And for this one, it would start low here and go up there. So you have kind of a lower slope. So if cows have less, if you're dealing with cows right now that have just lactated, what happened in the previous month matter less. than when you have cows that have lactated for longer periods of time, more than 79 days. So what they've done last time will be more correlated with what they will do this time. If they're cows that have just lactated, that relationship seems to be less strong. And then you just see that if they're younger, they will produce more milk regardless of what happened with the cattle last time. Yes? Okay. So it looks like milk production is higher for cows with less than 79 days, the red dots, but only for lower values of milk production in the previous month, right? They seem to be pretty overlapping for higher levels of milk production in the previous month. This suggests what we call an interaction effect. That is, the effect of one variable, here I79, depends on values of a second variable, here previous. I think we're talking differently here. The value of the variable previous production previous month depends on the value of a second variable, here I79, whether it's category 0 or category 1. Less than 79 days since last lactation, or more than 79 days. This is a case where it might be useful to include in the model both a general effect of I79, like fit two lines with equal slopes and different intercepts, and an interaction effect. Let the slopes vary as well. If the latter is significant, if the interaction is significant, it tells us that we, in practice, should have one line for each level of the variable, I79, and these lines will have not only different intercepts, like we saw in class with the book example, but also different slopes. So let's see how that plays out. Inferential statistics. Model 1. Include only main effect of previous and I79, similar to what we have done in class. So our first model, we will not include interaction. We will include previous milk production, and we will include I79 just as a main effect. We're just letting the intercept of the two lines vary. So what are the hypotheses we're going to test? Well, for the overall model, and go back and watch the video lectures so you understand what this is, the null hypothesis is that all model coefficients, the coefficients for the two predictors, is 0. And the alternative hypothesis is that at least one model coefficient is different from 0. And then we have hypothesis also for each coefficient independently. So we run t-tests for each one of them. Age 0 is that the coefficient for the previous variable, meaning the predictor previous month milk production, is 0. It doesn't, if I change previous milk production, there is nothing that I can predict will change in terms of current milk production. And the alternative is that that's different from 0. We're doing the same for the variable I79, days since lactation, coefficient is 0, right? The slope for that variable is 0 or different from 0. Now, here's the model. So we're going to save that model in this variable called milk model. And we'll do the LM function, just like we did last time. That's the dependent variable. That's predictor number 1 plus predictor number 2. Oops. Plus, I like to do space because it's less confusing. Then we have the data set, milk data. Okay? Then we're going to ask for the summary of the model. So the summary of the model. First, we're going to look at the overall model and interpret that. So we're seeing that we have an R-square adjusted of 0.62, which is pretty much the same as the actual R-square. And that makes sense because both variables are important. So these two should be pretty close together, right? So it's not penalizing for us including more than one variable because both of them are relevant. And the model is statistically reliable. So let's interpret this overall piece. At least one of the predictor variables is related to the response variable because, yay, the model is significant. It's not likely that all of the predictors, all of the coefficients of all predictors equal 0. and when the other variable in the model is held constant. So at least one predictor is related to the response variable when the other is held constant. Here is the F value, and we looked for the p-value, or R looked for the p-value in an F distribution with 2 degrees of freedom of the effect and 196 degrees of freedom of the error. The model explains 62% of the variance in current milk production. Now let's interpret the findings related to specific predictors. So we're rejecting the null here, right? We're rejecting the null. That none of these variables are relevant predictors of our interesting response variable, current milk production. Now, hypothesis tests for specific predictors. Both predictors are uniquely related to the current milk production, right? So when you hold when you hold I-79 constant, fix it at 0, say, you still see a change in current milk production based on what happened on the previous month. If you shift it to 1, you still see a change. So regardless of when you stabilize 1, you still see the contribution of the variable previous milk production to current milk production. Same thing, if you fix current milk production, there's still a difference between whether or not you have a bunch of cows that have just begun lactating or have lactated for more than 79 days. So both predictors are significant. Take a look. Less than 0.05, less than 0.05. So it's not likely to see a coefficient that is this large under the null hypothesis, that it is 0. It's not also likely that we'll see a coefficient of this size just for sampling error, if in reality it was 0. So let's interpret findings related to specific predictors. So in terms of hypothesis tests, both predictors are uniquely correlated. We're going to reject both null hypothesis 1 and null hypothesis 2. Let's remember what those are. Coefficient for previous is 0, not likely. Coefficient for I-79 is 0, not likely, right? Those p-values, less than 0.05. Now, estimates, intercept of this model. This one. Oops. This one. So if we look at I-79, our reference level is 0 because R is printing 1 here, right? So the intercept is the value of current milk production expected when in the previous month we had 0 milk production and average cows, I-79 was 0, right? Cows had less than 79 days prior to lactation. So that would be the expectation in that respect. So here is the interpretation. Estimated value of current milk production when previous milk production was 0 and I-79 was 0. Yes? Coefficient for previous, right here. We expect that for each unit change in previous milk production, we expect a 0.79, change in the current milk production, right? And for this coefficient here, and because this is a multiple regression model, we should say when I-79 variable is kept constant. When I keep this one constant, I expect this change in current milk production for each unit change in previous milk production. When I hold previous milk production constant, I expect that for, if I have a set of cows that have, on average, more than 79 days of lactation, then I will have less, 13 pounds less milk production than if I had cows with less than 79 days of production. Okay? All else in the model held constant, cows with more than 79 days produce 13 pounds less of milk than cows with more than 79 days since lactation. So let's write out the general equation and we'll look at equations when we come back, because this is almost 20 minutes of this video. We'll do one more in a little bit. See you then.